These are notes 4.7. We're going to do three things. We're going to use the multiplication rule for independent events to calculate probabilities. We're going to do calculate the probability of at least one event happening using the complement rule and the multiplication rule. And then we're going to determine if it is appropriate to use the multiplication rule for independent events in a given setting. Okay? So we had talked about how the multiplication rule said the probability of A and B happening was the probability of A times the probability of B, given that A has already happened, right? That was our rule for multiplication for AND statements. Okay? Now, what if they're independent? That means that one event doesn't affect the other, right? So A happening to B doesn't really matter. So if they're independent, we can just say it's the probability of A times the probability of B, because if they're independent, A has no difference, right? It doesn't have an impact on B, so it's just the probability of B. So this is our general rule if things are independent. Okay, so here's an example. Suppose Pedro drives the same route to work on Monday through Friday. His route includes one traffic light. The probability that the light will be green is 42%, yellow 3%, and red 55% of the time. Okay? So what's the probability that light is green on Monday and red on Tuesday? Okay, now, does knowing what it was on Monday have an impact on what it is on Tuesday? No, we're going to say that those are independent events. The probability of something here does not affect the probability of the next day. Okay? So what we do is we want the probability of a green on Monday and a red on Tuesday. Okay? So the probability of green we said was 42%. And the probability of red was 55%. So all you do is multiply those two together, and you get your overall probability of those two events happening. Okay. So next problem: what's the probability that Pedro finds the light red on Monday through Friday? So we want a red, and a red, and a red, and a red, and a red, right? Monday, Tuesday, Wednesday, Thursday, and Friday. We want every day to be a red. So the and one day is independent of the other, right? If it's red on one day, it doesn't really change the probability of red the next day. So the probability of getting a red overall is 55%. So the probability of getting red this day is 55%. Probability of getting red this day is 55, and it's the same for every day. Okay? And you multiply those all together, you get an answer of 0.0503. So there's about a 5% chance that we're going to get a red every single day of the week when we go through there. Okay, now this is kind of an interesting problem. In January 28, 1986, I was in 5th grade, and I was sitting on the floor, and we were watching a TV of the space shuttle taking off, the Space Shuttle Challenger, and it exploded upon takeoff. I remember that very vividly. Killing all 7 crew members aboard. Afterwards, scientists and statisticians helped analyze what went wrong. They determined that the failure of an O-ring joint in the shuttle's booster rockets was to blame. Experts estimated that the probability that one individual O-ring would proper functionally under the cold conditions would be 97.7%. So very high probability that it would operate correctly. But there were 6 of these joints, and if only one of those failed, then it blew up. Okay? So there were 6 of them on the shuttle. Assuming the O-ring joints succeed or fail are independent of each other, find the probability that the shuttle would launch safely under those conditions. Okay? So safely meant that we have 6 of them. We have 6 O-rings, and each of those have to be successful. So 0.977 times 0.977 times 0.977 times 0.977, and okay, so we multiply those all together. Now, a quick way to do that is 0.977 raised to the 6th power, right? Okay, so if you multiply all those together, you get an 86% chance that all of the rings will be successful. Okay, probability that all of them will be successful would be 87% of the time. Okay, now here's this idea of at least one. Okay, what's probably it's going to blow up? Okay, so the probability of at least one failure. Okay, so we have 6 rings, right? We could have 0 failures, we could have 1 failure, 2 failures, 3 failures, 4, 5, or all 6 could fail, right? So the probability of having at least 1 failure would be all of these probabilities right here added together. Now, we could find the probability of 1 failing, and the probability of 2 failing, and the probability of 3 failing, and then add all those probabilities together. That'd be a lot of work, though. So we use the complement rule. The probability of at least 1 failure is the same as 1 minus the probability of 0 failures. Okay, so if I can find this one, remember if we have all these different probabilities, if we take 1 minus these, it would give me this one, right? So we're doing 1 minus the probability of 0 failures. Okay, so how do you find 0 failures? Okay, 0 failures is what we just found up here. It was an 86% chance that it was going to be successful, right? 0. So this would be 1 minus 0.87. So there would be a 13% chance that at least one of them was going to fail. They found that that was way too high of a probability, so they definitely changed the O-rings and made them a lot more successful. So even though one of them independently had a very good probability of being successful, altogether not as high. Okay, so because we needed all of them to work all at the same time. Okay, so here's another problem for us to look at. Many people who come to clinics to be tested for HIV, the virus that spreads AIDS, don't come back to learn their test results. They get the test done, but they don't really know whether they have it or not. Clinics now use a rapid HIV test that give the results as the patient waits. In this clinic in Moali, they used rapid tests. They increased the percentage of patients who learn their test results. So it went from 69 people knowing the results to 99.7. So there's still 0.3% of the people that left and didn't find out. But most everyone knows, okay, whether their test was positive or negative. Now, the trade-off for that is that this rapid test is less accurate. Okay, the other results were better, but this is quicker and they know about it. Applying to people who have no HIV, one rapid test has a probability of 0.004 producing a false positive. So it's testing positive even though you do not have HIV. So if a clinic tests 200 randomly people who are free of HIV, okay, there's 200 people there that don't have HIV, what's the chance at least one of them will test positive, a false positive? Okay, so we could have 0 people test positive, or 1, or 2, or 3, or 4, all the way up to 200 people testing positive. Okay, now what I want to find is the probability of at least 1 false positive. So at least 1 would be 1 or 2 or 3 or 4 or 5, right? All of these. I want to add all those up together. I want to find this probability. So probability at least 1 is this right here. Okay, now, and that's a lot to find, so the easier way to do it would be 1 minus the probability of 0. Okay, so how do I find the probability that there were 0? Okay, there were 0. So we have a 0.004 chance of testing positive. That means we have a 0.996 of testing negative correctly. And we need that to test negative correctly 200 times so that nobody has a false positive. So if I multiply this together by itself 200 times, that's the probability of 0 of them. Okay, so think through that. This is the probability that they test negative, and I need all 200 people to test negative. Okay, and if I find this, I work this out, I get 0.5514, it says. Okay, so this right here is the probability of at least 1. Okay, 1 minus this will give you this. So there's a 55% chance that if using this rapid test, at least one person will have a false positive. They'll test positive even though they're not. So they have to do some follow-ups with it. Okay. Okay, so now we're going to talk about this independence rule. So basically, we're going to make a decision when I have to use this formula versus this formula. And the difference is whether they're independent or not, right? Okay. So this is a cartoon here. Very interesting. What are the odds of two ropes breaking at exactly the same time? Okay, so they're in the middle here. What's the probability of two ropes breaking at exactly the same time? Now, is this event breaking independent of this event breaking, or because this broke, this one's more likely to break too? Okay. In this particular cartoon, they are not independent events because we got people standing in the middle, right? So if they're very heavy, the probability of this happening kind of affects the probability of this happening too. Okay, they're linked to each other, they're not independent of each other. Okay, so here's a problem for us to look at. Government data show that 8% of adults are full-time college students and that 30% of adults 55 or older. If we randomly select an adult, P is a full-time student and over 55, can I multiply those together? Okay, so we have to think, can I use this rule or not? Can I just take probability of a college student and multiply it by the probability that they are over 55? No, I can't, because there are some people that are I'll just read this here. So because being a college student and being 55 are not independent events, knowing that somebody's a full-time college student makes it a whole lot less likely that she or he is over 55, right? So the probability so what you should do is think about, if I want an and statement, the probability that they're a college student or not a college student, the probability that they're 55 or not over 55, okay? If I know that it's a college student, I can't just take this times this, because the probability of somebody being 55 and a college student, not very high, right? Okay, so there are not independent events. Knowing that somebody's a college student tells me something about their probability of being over 55. Okay, so let's look at another example. Okay, going back to the gender and ear pierced, right? Okay, A is male, B is ear pierced. Are the two events independent? Okay, so male and ear pierce. So male and ear pierce was 19 out of the 178 people. Okay, now if I take the probability of A, probability of male times the probability of ear pierce, probability of male was 90 out of the 178, and ear pierced was 103 out of the 178. If I multiply those together, I get this. That tells me that they are not independent events, right? Because if they're independent events, those should kind of be the same thing. Okay? So, is there a connection between mutually exclusive and independent? So let's think about what these terms mean. Okay, mutually exclusive meant that things cannot happen together, right? Okay, mutually exclusive. If one event happens, the other event does not. And independent means if one event happens, it doesn't impact the probability of the next event. So let's start with another example here. Okay, choose somebody randomly in the U.S. Event A is that they're male. Event B is that they are pregnant. Okay, event A is male, event B is that they're pregnant. It's very clear that these two are mutually exclusive, right? They can't happen together. You can't be a male and pregnant at the same time, okay? So that they're mutually exclusive events. Are they also independent? Okay. Well, does knowing A, right, if I know that somebody is a male, does that change the probability that they're pregnant? Of course, yeah. We know that right, it's 0, right? Or the overall population, I don't know what percent is pregnant, but it's like knowing whether you're male or female definitely has an impact on whether you're pregnant or not. So they are not independent. and here's a thing here to think about. Two mutually exclusive events, okay, that two events that cannot happen together can never be independent, because we know that if one thing happens, it guarantees that the other will not happen. Okay, think about that, pause it and think about that again. If I know that two things do not happen together, okay, they're mutually exclusive, they can never be independent, because I know if one event happens, I know the other probability of the other one is 0. Okay, so one more example. The first trimester screen is a test given during the first trimester of pregnancy to determine if there are any specific chromosomal abnormalities in the fetus. According to a study published in the New England Journal of Medicine, approximately 5% of normal pregnancies will receive a positive result. So even though they're normal, they get a positive result. That said, there's something abnormal. Assume that test results are for individual women are independent. From women to women, one doesn't impact the other. Suppose that two unrelated women who are having normal pregnancies, these two women, are given the first trimester screen. What is the probability that Devondre gets a positive result and Miranda gets a negative result? Okay, so a positive result would be 5% of the time, and a negative result would happen 95% of the time. So if you take 5% times 95%, there is a 0.0475 chance that she gets a positive and she gets a negative. Okay, number 2. If 100 unrelated women with normal pregnancies are tested at the trimester, what's the probability of at least one receiving a false positive? Okay, so we have 100 women, so we could have 0 or 1 or 2 or 3 or 4 all the way up to 100 women test positive. So the probability of at least one, okay, we're looking for this probability right here, right? That's what we want to find. So the idea to get that, instead of finding each individual one, we're going to do 1 minus the probability of no one getting a positive. Okay, so I have 100 women. Okay, if they don't get a positive, the probability of getting a positive 5, probability of not getting a positive is 95, and I need to do that for 100 women. So I'm going to take 0.95 raised to the 100th. That's the probability that all 100 of them would not be positive. Okay, so 0.95 raised to the 100th power is 0.0059, and 1 minus this answer gives us 0.994. Okay, so there is a 99.4% chance that at least one of the women with normal pregnancies is going to get, if we take 100 women, at least one of them, a 99% chance at least one of them is going to get a false positive. Okay, that's really, really high. Okay, so we did a couple things. Okay, we looked at the multiplication rule. If they're independent, just multiply event A times event B. Looked at the probability of at least one using the complement, right? 1 minus what we're trying to find. And when is it appropriate to use that multiplication rule? If they are independent, we can just multiply them together.